Okay, so here we're going to look at arrangements involving restrictions, and really students tend to find these problems quite hard because there's no one way to go about answering any one of these questions. It's really just about stopping and thinking quite logically. A pigeonholing technique is really useful in these sorts of problems in many cases. So let's get straight into some examples. So we have 3 boys and 3 girls that are to be seated in a row. In how many ways can this be done without restriction? So if there's no restrictions on how the 3 boys and 3 girls can be seated, we essentially just have 6 people that need to be seated in a row. So we know from our previous video that there are 6 factorial ways that that can be done, and 6 factorial is 720 different ways that these girls and boys can sit in a row. Okay, then in how many ways can it be done if there is a boy at each end of the row? Okay, so if we think about the fact that we're going to have 6 people seated in a row, and we need to have a boy at each end. A boy and a boy. So whenever you're dealing with problems involving restrictions, you want to think about dealing with the restriction first and then working out how everyone else is going to fit around it. So we need to put a boy in the first position, and there are 3 boys to choose from, so there are 3 different options that could go here. Then once we've put a boy in the first position, we also need another boy in the last position, so there's 2 remaining boys to choose from to go here. Now there's no restriction on how these 4 people in the middle here are going to be seated, and so there's simply going to be 4 factorial ways that we can arrange them. Again, we need someone in every seat, so this is a multiplication situation. So we have 3 times 4 factorial times 2 different ways that we can arrange the girls and boys. So that comes to 144 different possible arrangements. Same problem, 3 boys and 3 girls are to be seated in a row. In how many ways can this be done if boys and girls occupy alternate positions? Okay, so there's sort of 2 ways to think about this kind of problem. Okay, so the first is, alright, again in both cases we're going to think about our 6 positions and how we might logically think that through. So we've got 6 positions, and we need to alternate. So we need those 3 people to be, let's say, not those 3. Let's fix that. Those 3 people to be, let's say, girls. And we need those 3 people to be boys. So there are 3 factorial different ways that we can arrange the 3 girls, and 3 factorial different ways that we can arrange the 3 boys. Now there's one other thing that we haven't thought about in this situation, because we've assumed that we're going to start with a girl. So obviously we could have this exact same situation, but instead starting with a boy. So there's going to be 2 different ways. We're going to multiply our options by 2, because that would be when we start with a boy instead. So starting with a girl, there'd be 3 factorial times 3 factorial different ways for that to happen. Starting with a boy, there'd be 3 factorial times 3 factorial different ways for that to happen. So we have 2 times 3 factorial times 3 factorial. We know 3 factorial is 6, so that's 2 times 6 times 6, so 72 different ways. The other way we can think about it is, again, thinking about our little pigeonholes and what options have we got for each one. Okay, so if we think position by position, so the first position, any of the 6 people could sit here. Boy, girl, doesn't matter. Then in the second position, it has to be, so let's say, for example, a girl was sat in the first position, then it would have to be one of the 3 remaining boys in the second position. Or let's say we sat a boy in the first position, then it would have to be one of the 3 remaining girls in the second position. Either way, there's 3 different options here for the second position. Okay, so then we've now seated 1 boy and 1 girl. So there's 2 different options for the next position and 2 different options for the next position, where we need to again seat a boy and a girl. Now we've got 1 girl and 1 boy left, and so they're going to each go into these 2 positions. So we have 6 times 3 times 2 times 2 times 1 times 1, which again gives us the same answer of 72 different arrangements. Okay, example 2. How how many 4-digit positive integers can be formed using the digits 6, 7, 8, 9 and 0 without repetition, if there is, first of all, no restriction. Now, these kinds of problems are fairly common, but what you need to be really, really careful about here is the fact that 0 is included in this set of digits that we're dealing with, because 0 has its own set of restrictions implied. Because we want to form a 4-digit number. Yes, there's no restriction, but it's not simply, we've got 5 digits to choose from, but it's not just going to be 5 factorial in this case because of the 0. So if we want a 4-digit number, we can't have 0 at the beginning. That wouldn't be a 4-digit number, that'd be a 3-digit number. So actually it means we've only got 4 options for what could go at the beginning. We're creating a number without repetition, so I've put a number in the first position, I can't use that again. But I can use the 0 now, so I've got 4 different options again at the second position, then I've got 3 options, and then I've got 2 options. So 4 times 4 times 3 times 2, let's go to my calculator quickly, 4 times 4 times 3 times 2 is 96 different options with no restriction. Bearing in mind that no restriction is a loose statement given that 0 itself implies some restrictions. Okay, same problem, 4-digit positive integer formed using the digits 6, 7, 8, 9 and 0 without repetition if the number has to be greater than 8,000. So again, we want a 4-digit number, but here it has to be greater than 8,000. So that means there's restrictions on here. That one can be only 8 or 9. So we've only got 2 options to go there, and then we can put anything after that. Again, it's without repetition, so we've put 8 or 9 in the first position. That leaves us with 4 different digits to choose from here, 3 digits to choose from here, and 2 digits to choose from here. And so we've got, 8 times 3 is 24, times 2 is 48 different options to create a 4-digit number greater than 8,000. Okay, part C. Same problem, 4-digit positive integer formed using the integers 6, 7, 8, 9 and 0 without repetition if the number is odd. Okay, so if we've got an odd number, the restriction is on here. So that means that has to be an odd digit for the total number, for the whole number to be odd. So that means that digit has to be 7 or 9. So we've got 2 options that can go there. Then we worry about filling in all the other spots where there aren't restrictions. Again though, there is a restriction at the first digit, so we have 4 digits remaining to put in the first position, but one of those 4 digits is 0, so we actually only have 3 digits that could go in the first position. Then we've got 3 digits remaining, they can all go in the second position, and 2 digits remaining, they can all go here. Again, we want a number in each of the 4 positions, so it's an AND situation, so we're multiplying. 3 times 3 times 2 times 2, it's 9 times 4, so 36 different options. And part D, how many 4-digit positive integers can be formed using the digits 6, 7, 8, 9, 0 without repetition if the number is even? Okay, so the best way to think about this is there's a couple of different ways, and this can be quite a complex problem starting from scratch. Given that we've just worked out the number of options where the number is odd, we're actually quite a long way along the way to answering this problem. I'm just going to flick back here to get some of our answers we need. So we worked out in part C that there are 36 odd numbers. In part A, we worked out that there are 96 numbers in total that could be created. So what we find is that there are 96 numbers. We want the total number of options minus the odd options, which means that is 96 minus 36, and so that means there must be 60 even options. So that's definitely the quickest way to go about that. If though we hadn't worked out the number of odd options already, then we need to think about the number of even options. And again, the 0 in this problem makes things quite difficult. We really need to think about 2 different cases. The situation where the number ends with a 0, which would make it even, and the situation where the number ends with 6 or 8 as 2 different things. So first of all, if we end with a 0, So we've got our 4-digit number. We're going to put the 0 at the end, so there's one option for the last number. The 0 is already taken out of the mix. We've got 4 digits remaining, and any of those 4 digits could go at the beginning because 0 is already taken care of. Then we've got 3 different options here and 2 different options here. So there are 24 different 4-digit numbers that end with a 0. So they're all even numbers. Then we need to think about ending with the non-zero even numbers. So in this case, that is 6 or 8. So in this situation, we've got our 4-digit number. There are 2 options for what we could put here. Now this time, 0 is still in the mix of the 4 different digits remaining. So I only have 3 options available for the beginning. I still have 3 digits remaining. 3 of them could go, any of them could go here. Now I have 2 digits remaining. 2 of them could go here. And so we've got 36 different options here. The number is either going to end with a 0 or end with a 6 or 8. So that means that we're going to add together 24 and 36 to find that we get 60 different arrangements. So you just need to be very careful when your when your list of digits includes 0, because 0 can't go at the beginning of a number if it's to be 3 or 4 digits. So you need to think quite carefully about that. Okay, example 3. In how many ways can the letters of the word grouped be arranged if there is no restriction? Okay, so we have 7 different letters. So if there's no restriction, 7 factorial different ways we can arrange them. So 5,040 different arrangements. In how many ways can the letters of the word grouped be arranged if the letters P and D must be next to each other? Okay, so what we've got happening here is we have to have the P and D next to each other. So we've sort of got 2 letters grouped together. And there are 2 different ways we could arrange those, 2 factorial, which is 2. So then the other 5 letters need to be arranged around here. So some of them might be at the beginning, some of them might be afterwards. So what we essentially have here is we're grouping the P and D together, and there are 2 different ways that they can be arranged. And then treating the P and D as one entity, we now have 6 things to be arranged. The group with PD in it and the other 5 letters can all be arranged in 6 factorial different ways. And then for each of those 6 factorial different arrangements, there are 2 different options because we could have P and then D or D and then P within that. So the total number of arrangements is 2 factorial times 6 factorial, which is 2 times 720, which is 1440. In how many ways can the letters of the word grouped be arranged if the vowels must be next to each other? So this is essentially the same problem as before. We have 3 vowels in this word, so we're going to group those 3 vowels together. And there are 3 factorial different ways the vowels can be arranged. And then we have 4 other letters around them, or after or before them. So then we need to think about how many different ways can we arrange those 5 things, which is 5 factorial. So we're going to have 5 factorial times 3 factorial, which is 120 times 6, so 720. In how many ways can the letters of the word grouped be arranged if the letters P and D must not be next to each other? Okay, so this is where it's useful that we've already worked out, and in fact, even if I was given this question without having been asked part B, I would probably still find how many different ways can I do it with P and D grouped together, and then subtract that from the total number of arrangements. So we know, let's flick back to our previous parts. In part A, we worked out that there are 5,040 different arrangements, and in part B, we worked out that 1,440 of those arrangements have P and D together. So that means that we need the total number of arrangements minus the arrangements with P and D together. And so that was 5,040 minus 1,440, which gives us 3,600. Different arrangements where P and D are not next to each other. Last part of this question, in how many ways, it should be part E, apologies, in how many ways can the letters of the word grouped be arranged if the vowels are together and the consonants are together? Okay, so previously in part C, when we looked at having the vowels together, we were arranging the consonants in any way around them. So, for example, in the diagram I've got drawn here, the consonants are not together. So, we need to think about the fact that we want the vowels to be together. So we've got 3 vowels. They can be arranged in 3 factorial different ways. And we also want the consonants together, so and they can be arranged in 4 factorial different ways. But then obviously we could also put the consonants first and the vowels second. So there are 2 different ways that we could arrange those 2 groups. 2 factorial, which is 2. So we've got 3 factorial times 4 factorial times 2, which is 6 times 24 times 2, which is 288 different arrangements. So in summary, there's not really new techniques here, but it is really important to stop and think logically, and I find a pigeonholing sort of technique works extremely well. Draw out a series of boxes, think about how many options there are for each boxes. Consider the restrictions first. So in some of the problems involving the 4-digit number, we had restrictions on the last digit. Doesn't matter that it's the last digit, that's where the restriction is. Consider how many options there are for that digit first, then work your way through the rest of the question.